Till now, we have discussed all the types of algebra involving complex number. Let us move further and have a look how to express any given complex number, say minus 5i times 1 upon 8i in the form of a plus bi, and how to find the modulus and conjugate of a given complex number. That's what we will be looking in today's video. Let us first have a look how to express any given complex number in the form of a plus bi. To understand it, we will be considering an example and I will tell you step by step how to do that. The example we took is minus 5i times 1 upon 8i. So the first step is to open the brackets and simplify it as much as we can. So it will look like minus 5i square upon 8. And as we know, in the second video itself of the complex number, I told you the value of I square is minus 1. So replacing I square with minus 1 gives us minus 5 times minus 1 upon 8. And very basic mathematics, it is very basic that we know minus 5 times minus 1 will be 5 upon 8. Here, so we get 5 upon 8. So this is our real part. Or since no imaginary part is remaining here, so we write plus I0 because the coefficient of imaginary part I is 0. So we write 0 here. Let us consider one more example. We are provided with 5 minus 3i whole cube and we are asked to express it in the form of a plus ib. So after looking at the question, the first and foremost thing that strikes to my mind is a minus b whole cube. And in the last video itself I told you that in the complex number also we have such properties a minus b whole square, a minus b whole cube, a square plus b square. We have such properties also here also. So basically our first step is to apply that property here. What's that property? That's a minus b whole cube, which will be equal to a cube minus b cube plus 3ab square minus 3a square b. So we'll be using this property because 5 minus 3i whole cube is of the form a minus b whole cube. A will be replaced by 5 and b will be replaced by 3i. So let's do it. On doing so, we get 5 cube minus 3i whole cube plus 3 times 5 times 3i whole square minus 3 times 5 square times 3i. So now, let us cube and square the terms and we get 125 minus 27i cube plus 15 times 9i square minus 9 times 25i. So, we have already studied that the value of I square is minus 1 and the I cube is minus I. So before that, let us simplify it more. We multiplied all the values and now we have to replace the values of I square and I cube with minus 1 and minus I respectively. And doing so we get 125 plus 27i minus 135 minus 225i. And on further simplification, we get our final result that is minus 10 minus 198i. Let us look at a little bit complicated example. Minus root 3 plus root of negative 2 times 2 root 3 minus I. So as we can see, root of negative 2, we know that root of negative 2 or root of negative terms does not exist. So we made a new concept called concept of complex numbers. So we all have already studied that root of negative 1 is equal to I. So using this, we can write root of negative 2 as root 2 times I. So the equation will be minus root 3 plus root 2I times 2 root 3 minus I. So now the next step is to open the brackets. We will be multiplying minus root 3 with 2 root 3 and with minus I. And next step is to multiply root 2i with 2 root 3 and with minus I. By doing so, we get minus 6 plus root 3i plus 2 root 6i minus root 2i square. And we know that the value of I square is minus 1. So replacing the value of I square with minus 1 and simplifying the given equation, and separating the real and imaginary part so as to look it in the form of a plus ib. So the final result we get is minus 6 plus root 2 plus root 3 1 plus 2 root 2 I. Minus 6 plus root 2 is our a real part and root 3 1 plus 2 root 2 I is our imaginary part. I hope you have understood the concept of expressing the complex number in the form of a plus bi. Let us now move further and have a look how to calculate modulus and conjugate of a complex number. Let z equal to a plus ib be a complex number. Then the modulus z is denoted by mod z and it is equal to root of a square plus b square. And the conjugate of z is denoted by z bar and is equal to a plus ib. Only the sign in the conjugate, only the sign of imaginary part will be changed. So this is how we calculate the conjugate and modulus of a given complex number. Let us have a look over a few examples so that we can understand it better. We have z equal to 3 plus I and we need to calculate the modulus and the conjugate of the given complex number z. So as we have already studied, the modulus of any complex number z is equal to root of a square plus b square. And we can see that the value of a is 3 here and the value of b is 1 here. So let us replace the a with 3 and b with 1. So we will get z equal to root of 3 square plus 1 square, which will be equal to root of 10. So now we have to now calculate the conjugate of the given complex number. So we know that the conjugate is equal to a minus ib, which means we have to change the sign at the imaginary portion. So here we have 3 plus I, so which means we have to change the sign for I. So it's plus now, we will change it to minus, and if it is minus, we will change it to plus. So it will be equal to 3 minus I. Now let me tell you something interesting. Do you remember the formula to calculate multiplicative inverse of a given complex number, say z? If not, let me tell you the formula first. The formula was z inverse, or we can say 1 upon a plus ib will be equal to a upon a square plus b square plus I minus b upon a square plus b square. So here we can see the denominators are same, so we can take the LCM and write it as 1 upon z equal to a minus ib upon a square plus b square. As we just now studied that the modulus is equal to under root a square plus b square. Squaring both sides gives us mod z whole square will be equal to a square plus b square and the conjugate is equal to a minus ib. So replacing the modulus and conjugate in the formula of multiplicative inverse, it gives us 1 upon z equal to conjugate upon modulus. So it can be written as z times conjugate of z equal to modulus of z times whole square. So using this formula also you can calculate the multiplicative inverse very easily. Let us look at small example how you can use this formula to calculate multiplicative inverse. We have z equal to 2 minus 3i and we need to calculate the multiplicative inverse of the z. So to do that we have two methods. The first one is using conjugate and modulus and the second method is using direct formula. We will be doing this problem by both the methods so that you can see both the methods give us the same answer. So first using conjugate and modulus. So as we know the conjugate is equal to a minus ib, which means changing the sign at imaginary part. So for this, the conjugate will be equal to 2 plus 3i. Similarly, we will be calculating the modulus for z. Modulus is equal to a square plus b square. So we get 13 for this. And now, as we have already studied z times conjugate of z, it will be equal to modulus of z whole square. So rearranging the formula so that we can get the multiplicative inverse, it will be looking like conjugate upon modulus square. So putting the values we get 2 plus 3i upon 13, which will be our multiplicative inverse. So now let me solve the same problem with the formula that we have already studied in the previous videos. So the formula was a upon a square plus b square plus I minus b upon a square plus b square. So putting the values of a as 2 and b as minus 3, b as 3, we get b as minus 3, we get 2 plus 3i upon 13. So you can see the method we have used does not affect the final result. The result in the both cases are same. So you can use any one of them, whichever you feel like doing. Let us have a quick glance over some results which will be very helpful to you while solving the questions. The first result is modulus of z1 z2 will be equal to modulus of z1 modulus of z2. Both the sides are same no matter where the modulus is. The next is modulus of z1 upon z2 will be equal to modulus of z1 upon modulus of z2. The condition here is z2 modulus of z2 should not be equal to 0. If it is so, it becomes division by 0, and you know division by 0 is not allowed. So next is conjugate of z1 z2 will be equal to conjugate of z1 times conjugate of z2. Conjugate of z1 plus minus z2 will be equal to conjugate of z1 plus minus conjugate of z2. And the last one is conjugate of z1 by z2 is equal to conjugate of z1 by conjugate of z2. Here, same condition we have is conjugate of z2 should not be equal to 0, and you know the reason. So this was all about representing complex number in the form of a plus ib and the modulus and conjugate of a complex number. So in upcoming videos, we'll be learning arc and plane and representation, polar representation of complex numbers.